Awesome. Great to be here, everyone. And I'm here to talk about operating Postgres logical replication at massive scale. This is my third talk. I'm trying to keep up the energies, but I'm most excited about this talk because this is what I've been working on over the past couple of years now. So before I get started, I'll quickly introduce myself. I'm Sai, and I lead all the Postgres efforts at ClickHouse. And prior to ClickHouse, I was the CEO and co-founder at PeerDB. And PeerDB was a data replication product which was built with laser focus on Postgres. Right? We made it very easy to sync data from Postgres to external data stores, and ClickHouse was one of them. And which is why ClickHouse acquired PeerDB around 2 years ago. That's how myself and my team joined ClickHouse. And prior to PeerDB, I worked at Microsoft in the Azure Postgres team for around 4 or 5 years. And I have a few colleagues, ex-colleagues who joined the talk, and thank you so much for the support as always. And prior to Microsoft, I worked at Citus Data. I was an early engineer, and Citus was a distributed Postgres database, right? And I saw it go through the Microsoft acquisition. And so overall, my Citus plus Microsoft tenure was around 8-9 years. Basically, that's where I learned a lot about Postgres. So my life has been mostly in Postgres and ClickHouse and open source databases. So before I get started, this is something that I have been doing across all my talks, but how many of you have heard about ClickHouse, basically? So amazing. I see around 60%. Yesterday it was 90%. So, but yeah, interestingly, when I used to deliver talks few years ago, it was more 10-20%. Now it's grown quite a bit. So that's good to see. So ClickHouse is an open source column-oriented distributed OLAP database. It started as a project in 2009 and went to production in 2012 and was supporting the second largest web analytics platform in the world. It was open sourced in 2016, and since then has been adopted by many large companies like Netflix, Instacart, Meta, Anthropic, OpenAI, and many companies. In 2021, ClickHouse Inc. was formed, and the idea was to provide a seamless way for customers to deploy and manage ClickHouse in the cloud, right? And number two, ClickHouse is a column-oriented database with many specialized features and optimizations around blazing fast analytics. Number three, it is distributed. It comes with sharding in the open source and separation of storage and compute architecture in the cloud. It is multi-master, and also there is a cross-region setup that you can do with ClickHouse. Last but not the least, it is a purpose-built database for analytics, basically, right? How Postgres is an open source database purpose-built for transactions, ClickHouse is the other side of the coin, which is it is purpose-built for analytics, supporting aggregations, real-time visualizations on massive data sets. So before we get started, I would love to cover a few concepts that will be important for this talk. First is I would love to give a quick primer on what is Postgres change data capture. And I'll use CDC as the shortcut of change data capture because my life will be easy. Postgres CDC represents a logical stream of changes as they occur in Postgres that external clients can consume and get a consistent snapshot of Postgres in that point in time. So that stream of messages contains commands like inserts, updates, deletes, schema changes, which are nothing but relation messages under the covers, right? Clients can continuously consume these messages and maintain a consistent snapshot of the Postgres database. Postgres CDC powers many real-world use cases. For example, it lets you replicate data from Postgres to external data stores like ClickHouse for real-time analytics, Kafka for real-time alerting. It also supports Postgres to Postgres online migrations. It also supports Postgres to Postgres online version upgrades, and a bunch of other use cases. So let's double click on a few Postgres-specific concepts, right? We are here to talk about logical decoding and logical replication. So let me define what that is. Logical decoding, also called as logical replication, right, is the technical mechanism behind Postgres CDC. It helps transform the Postgres transaction log, which is the write-ahead log, as you folks know, into a stream of meaningful changes that Postgres or external systems can understand. these are the changes with like transactions with like these inserts, updates, deletes, like the schema changes which are relation messages and all of that, right? Next, let's talk about logical replication slot. And logical replication slot is the building block of logical decoding and logical replication, right? And logical replication slot captures changes happening in Postgres through the write-ahead log, right? And enables streaming of the write-ahead log in a logical format to the client. Under the covers, it basically keeps track of the write-ahead log that is consumed by the client and that is yet to be consumed by the client, right? And there are pointers like restart LSN and confirm flush LSN, which is what logical decoding uses to decide what is like flushed, if a restart happens, from where should I start, and all of that, right? So at a high level, logical replication slot is a data structure that keeps track of the write-ahead log in an understandable format to the client, right? And then physical replication is like more binary representation, and like clients can't understand that, right? It's only Postgres can understand that. So one important thing to note is logical decoding is tightly coupled with the Postgres process, basically. So consuming changes requires an active database connection, right? And Postgres retains the write-ahead log until the client acknowledges that like until this LSN I have like consumed all the messages, right? Now if the replication slot isn't actively consumed, the write-ahead log can start piling up, eating disk, and even crash Postgres, right? So that is one important thing, that logical replication and logical decoding is very tightly coupled with the Postgres process, basically, right? Hence Postgres change data capture and like logical replication is fragile and needs to be handled with care, right? And that's the reason we were even able to build a company out of this like important concept, right? One thing I'd like to call out here, this is one observation that I added last minute in my slide deck, is bin log replication in MySQL is different from Postgres logical replication and Postgres logical decoding. I feel it's a bit more mature. That's a controversial take, but like it is a bit more mature. The reason is because in MySQL, the bin log in bin log replication, right, transactions are ordered, right? Say if you have like two transactions T1 and T2, and you have a bunch of statements within that transaction, right? The bin log like groups all these like statements and groups the transaction at one place. You have T1 with all that group, T2 with all that group, right? So when clients are consuming it, right, they just read it like sequentially, and then they get the like changes happening in MySQL, right? In Postgres, it is different. In Postgres, like all of these transactions in the write-ahead log can be interleaved, right? So you have all these like statements like begin, insert, update, commit, right? Across all these like transactions, they can be interleaved, right? By which when these clients try to read the logical replication slot, it's not a sequential process. It needs to go front, back, decode the transaction on the fly, and then send it to the client, right? So overall, logical decoding from that perspective also is fragile, right? That's the reason in when you look at stat activity, right, like you will see like stuff like reorder buffer and all of that, right, which is where it it's a complex data structure where like it forms the transaction before giving it to the client. So at a high level, Postgres logical decoding is fragile and needs to be handled with care. So here is an example of how logical decoding looks in action. So this is a Python client which is using start replication, right, which is reading the replication slot, right, and then that's the command, right, and that is fully streaming, right. So it always the connection is open and it continuously streams changes as it happens. So it's more like push based, right, and then that the second box that you're seeing is more like the client telling Postgres that, hey Postgres, I have read until this particular LSN, so you can go and flush the rest of the wall, right. So both of those steps are very, very important for like making logical decoding work. One thing I'd like to call out is in this talk, I'll be talking about logical decoding and like not specifically logical replication. Logical replication is more Postgres to Postgres, right? So here I'll be talking about more the basis of logical replication, which is logical decoding, right? So you could be thinking why ClickHouse uses Postgres logical decoding at scale, right? Like why are we like even like talking about this here, right? The reason is because one of the common reference architectures that we see across customers is that customers use Postgres and ClickHouse together to power their real-time customer-facing applications. They use Postgres for powering their transactional OLTP use cases, and ClickHouse for powering their analytical use cases, right? And the standard, the standard use cases, they start with Postgres, right? And Postgres powers both transactions and analytics, right? And quickly as the data grows, they see that the analytics is getting slower, the dashboards are slower, which is then they adopt ClickHouse, which is a purpose-built analytical database, right? And one of the standard architectural decision is they continuously replicate that data from Postgres to ClickHouse using Postgres CDC or Postgres logical decoding, and then makes those transactions analytics ready. And then you have these customer facing applications which use both Postgres and ClickHouse, Postgres for transactions and ClickHouse for analytics, right? So this particular reference architecture we see across thousands of customers, right? This includes companies like Instacart, like even the big ones, right? Sayara, who is a cyber security company in Israel, LC Waikiki, which is a retail company in Turkey. It's like the Flipkart of Turkey. So many companies follow this particular architecture. So now to make this easier for customers, right? We offer a managed service in our ClickHouse Cloud platform, which is called as ClickPipes, right? ClickPipes, what it does is it provides simple native ingestion from different sources. This includes database CDC, streaming sources, and object storage as well. So streaming sources includes Kafka, Redpanda, Warp Stream, etc. And object storage include S3, Blob Storage, Azure Blob Storage, and GCS, right? And now obviously you can expect Postgres is the largest source of ClickPipes, right? And we saw that kind of growth, and I'll get into the numbers very soon, right? So what we did was to make this reference architecture easy, right? We added the Postgres CDC connector in ClickPipes, which is our native ingestion service, right? And under the covers, all of it uses logical decoding. So here is a quick example, right? So here I have my source, Postgres source. I enter the credentials. This Postgres can be anywhere. It can be in the cloud. It can be RDS. It can be Aurora. It can be flexible server. It can be a self-hosted Postgres. I enter all that information, right? And then I pick and choose the tables. Here I'm picking the listings table, whatever, the other table, right? And then within a few clicks, right, the data is replicated to ClickHouse, basically, right? And you see this in ClickHouse. So the Postgres data is available in ClickHouse for analytics, right? And Postgres CDC has two important steps. First is getting the data that is already present, right? You have a terabyte table. That data should be present, right? And the second is it also continuously replicates changes as they happen in Postgres, right? And all of this is taken care internally by the service, and it uses logical decoding under the covers, right? And replication slots under the covers. So here is the scale that we are talking about, right? So since the time we got acquired, right, we had around a handful of customers in production replicating data from Postgres to ClickHouse. Now, obviously, there was a lot of demand. Here I'm talking about production workloads, right? There were a handful of them. Within 1 year to 3 months, right? 1 year, 1.5 years, I would say. There are 500 plus customers running, Postgres CDC in ClickPipes in production, right? We move 300 terabytes, 350 plus terabytes of data. This is CDC data. This does not include initial load data. If you add initial load data, it will be again a couple of 200 terabytes or something like that, right? And that kind of accounts to 350 billion plus records moved, right? This was last month, and this again CDC. Overall, there are 1,000 plus databases that we handle. These are all customer databases across all these major cloud providers, right? And the scale that we are talking about is a single Postgres our largest Postgres database is 60 terabytes. This is not a sharded Postgres database. I'm talking about a single Postgres database close to 60 terabytes. And these are some customers, right? We have Wuling, which is an airline company. You have AutoNation, which is automotive company, right? Well-known company in the US. Some companies that are not called out are Sayara, right? They are a cyber security, fast-growing startup, right? A bunch of companies use Postgres CDC in ClickPipes, right? And then here is a testimonial from one of our customers, right? Where they talk about how it made their life easy, right? And they compare it with Debezium, if that makes sense. And I think that I love this quote because like it says, like whose goal in life is to transform bits into Postgres, bits from Postgres into ClickHouse. That was our life's goal for like last 3 years, where we transform bits from Postgres to ClickHouse as efficiently as possible to support this kind of scale. So now with that, like Postgres CDC, whatever I showed you, the demo, right, is fully powered by PeerDB, which is open source data replication product, right? Except the UI that you're seeing, right? All the underlying components, the entire like components are coming from PeerDB. So you can think of PeerDB as the open source project, ClickPipes as the managed service manifestation of like PeerDB, basically, right? So you can think of it that way. And even our deployments also, right? Like we read we basically deploy like releases directly from PeerDB, right? So it's like basically PeerDB is the OSS version and ClickPipes is the managed service version. So we kept it like very decoupled, and it has helped quite a bit on our engineering velocity, right? Because PeerDB has been evolving. If you look at our project, right, like every day there are multiple commits, right? So we maintain it very, very, very actively. So now that like we have understood few concepts of which is Postgres CDC, Postgres logical replication slots, and why logical decoding is important for ClickHouse, let's double click on what is the architecture that has helped us scale. So here is the architecture. So if you see, like this is the architecture of PeerDB or ClickPipes, right? Like both are kind of similar, right? And user interacts with ClickPipes using the UI, right? Or Open API, right? And I wish I had a pointer, I could have like pointed out, but yeah, user interacts with the product through the UI or Open API, which I didn't capture in this, but like I should have. And then from there, like there is a gRPC request which is sent to the Flow API. That's another infrastructural component, right? And the gRPC request basically has what is the source information, what is the target information, what are the tables that I want to replicate, right? Like simple information, it is sent to the Flow API, right? And Flow API forwards that gRPC request to Temporal, right? And Temporal is our workflow orchestration engine, and we are big fans of Temporal and we are heavy users of Temporal, right? And happy to talk about those experiences. Like we have our entire team sitting here, so if only you want to consider Temporal for your use cases, you can let us know and we can share our experiences, right? So Temporal is our workflow orchestration engine, right? And then below that, like there are two other important infrastructure components. One is the snapshot worker and the flow worker, right? Now, if you think about Postgres CDC, it has two important steps. First is initial load, get the existing data from Postgres to ClickHouse. Next is like the continuous load, which is CDC from Postgres to like ClickHouse, right? What snapshot worker does is it basically holds a persistent snapshot connection to Postgres, and we use that connection for a consistent initial load, basically, right? So it is required, and it's a very small component, but it's a very critical component to guarantee consistency, where we open a snapshot connection, right? We create the replication slot, open the snapshot connection, and then the flow worker basically uses that snapshot connection to get data from Postgres, right? And then stage it to S3. So we use like S3 and or GCS under the covers, right? And then we stream that to ClickHouse, basically, right? And initial load and CDC are kind of similar, right? Like flow worker is the hard worker, basically. It is what does the data movement, right? It is what like reads data, reads the replication slot if it is like CDC, right? And then it stages the data in S3 and GCS, and the format is also like Avro with ZSTD compression. So it's like very compressed, right? To save network cost, to improve like the efficiency, right? And then there is a asynchronous process which reads, the data from S3 and pushes it to ClickHouse, right? And one thing I called out, which is very important here, is the pull from Postgres and the push to ClickHouse are asynchronous. They are decoupled, right? And I'll tell you the importance of that in my future slides, basically, right? So if you see, each of these components, right, are stateless and horizontally scalable, right? So you can scale them as much as possible because they are all stateless. We keep the state in a catalog database, basically, called as, it's called just the catalog, PeerDB catalog, and that keeps all the state, right? Like, okay, in initial load, how many partitions are done, what is my like gRPC request, what is my LSN, all that information is stored in the Postgres catalog, right? And what we do is like every time a customer requests a pipe, we deploy this entire PRDB setup for them. So there is one, this is not a fully multi-tenanted architecture that way, right? It's basically we provision one entire cluster of this, right, per customer, right? And the customer can have multiple pipes, right? They have like 10 pipes, that's okay. It will use the same infrastructure, but then it is one entire cluster per customer, basically. And then now let's double click into the state machine, right? So whatever we saw here is more like, okay, there are, it's infrastructural components, right? Each of this is like compute, basically. Now let's double click into what is the state machine that we use under the covers, right? So, and this is what like temporal manages, right? So the first state is something called as the setup flow, right? Whatever you are seeing there. What does the setup flow basically sets up the entire replication job, right? It, you know, basically creates the publication on Postgres, it creates the replication slot on Postgres, right? It does the translation and of the tables in Postgres to ClickHouse with the right, like, you know, schema and all of that, right? So it takes care of that, right? So it basically sets up the entire like replication job, right? The second is we have something called as the snapshot flow. Snapshot flow is basically the middle one, right? The orange one. Snapshot flow is the one that is responsible for the initial load, right? And then it has two substates. One is the snapshot transaction, and then you have the partition initial load, right? Snapshot transaction is this single connection to Postgres, which ensures the initial load is consistent, right? It's always there. It's hooked to Postgres, always there to make sure that we read a consistent state. And then you have like the partition initial load, which basically partitions these large tables based on CTIDs, right? I'll talk more about that like soon, but we partition like these large tables logically based on CTIDs, right? And then we parallelly stream a bunch of partitions to ClickHouse, right? Now, if you see that partition initial load is a loop, right? Like it's a loop. There are multiple states there, right? Where we basically replicate few partitions at a time, basically, right? And the advantage of this is, if for example, I have a separate slide for that, is the advantage of this is, if for example flow worker dies, right? We don't need to restart everything. We know already what partitions are done and what partitions need to be done, right? So it's basically we do it in a way that like it's all, we don't need to restart everything again, right? So once the initial load is done, you have CDC running, right? And CDC running is the state which is responsible for consuming the replication slot basically continuously and without giving up the connection, and then replicating that to S3 basically. And then you have the normalized loop, which is an asynchronous job, which reads from S3 and then pushes it to ClickHouse basically, right? And targets change, right? If the target is Postgres, if you're doing Postgres to Postgres like replication, we don't use S3. We just do disk spooling, right? Like we just like store the, you know, changes on disk, right? We don't use any Kafka or anything, right? Like we don't want to make the architecture complex from that perspective. We just do disk spooling, right? It's not bound on memory. So like we do disk spooling. For ClickHouse we use S3. For Snowflake we use S3. For Kafka we directly shove it to Kafka because like it's like a, you know, it's a message buffer, right? So that's not a problem, right? So yeah, so this is the end-to-end state machine. Now the first question that you might get is this state machine too complex or modular, right? Because I keep hearing folks like building CDC with single binaries, right? And I'm not a believer of like that. I don't think it will work, and I'll get into why, right? So I feel the architecture is, you know, modular, and it is necessary for enterprise grade CDC. Here we are talking about production customers like running tens of terabytes of data, managing like mission critical use cases, right? So first, the architecture is, you know, that there is infrastructure isolation by design, right? So all these like components that you saw here, right, which is these, right, are isolated, by which you can, you know, failures or scaling events of one do not cascade to the other, right? So for example, the UI fails for whatever reason, it's possible, right? Like I send like some crazy request and it could like go down. Flow API goes down for whatever reason. The flow worker is still active and consuming the replication slot, right? And that's the heart of CDC. If you don't consume the replication slot, it can go and crash Postgres, right? So infrastructure isolation by design is one thing that we get. Second is there is independent scalability, right? So each of these components can be scaled based on what resources it needs, right? UI we give some 0.1 vCore, right? Whereas like for flow worker we give like 90% of the CPU because that's the hard worker, right? And so we get that flexibility of allocating resources based on the job they do, right? And then each of the state is idempotent and retriable. This is a very important thing, right? where typically these jobs, right, when you do an initial load of 10 terabyte table, right, recently we had a customer who did a 60 terabyte load, right, and then it took 4 days because they used less parallelism. We can even do it in like few hours, but they used less parallelism, right. These large jobs, if things fail in between, you want to recover, right? You don't want to start again. 4 days, like you don't want to waste them, right? And it is possible that like flow worker can like run into out of memories, right? Like for whatever reason, like the row is big or whatever, like you need to tune the batch size, things can like break, right? The advantage of this architecture is all the states that you saw are idempotent and retriable, by which you don't need to restart everything from scratch. You can just, continue from where it left off. Then we try to decouple workflows as needed. The big one is reading data from Postgres replication slot and shoving data, reading data from Postgres replication slot to S3 and then from S3 to ClickHouse. Those two workflows are basically decoupled. The advantage of this is tomorrow for whatever reason ClickHouse is down, right? We don't want replication slot consumption to stop, right? By decoupling that, like we always consume the replication slot and put it to S3, right? And once ClickHouse is up, the normalized loop will start and then start like backfilling that data to ClickHouse. Other thing is end-to-end observability via temporal, right? And temporal is a bliss in regards to state machine handling, right? So each of these states that you're seeing here is all workflows in temporal, basically, right? So we basically get end-to-end observability. Temporal gives like what are the input requests, how much CPU was used, where the error came, and all of that, right? So whenever like there are on-call incidents, right, temporal has been very helpful where we can go and see, okay, what failed, in which attempt it is, in my retries, like, is it like next retry, is it going to be in 5-10 minutes? So it gives all that information basically, which has been very, very important to us. And last but not the least, the entire architecture, right, is Kubernetes native architecture, right? So it is naturally aligned with like Kubernetes primitives, right? Like all of these are like pods under the covers, which has made our life, very easy with respect to deployment, scaling, operational management, right? And we have our Kubernetes and infrastructure expert Kunal, who is sitting here, and he single-handedly built our like entire managed service, basically, which now supports like 600 plus customers, right? So, and the reason is like Kubernetes, basically. Now, what I'll do is basically I will go into, so far we talked about architecture, right? There are other important decisions which are critical to handling this scale. So the first decision is purpose-built for Postgres. This was the entire like unique insight of our company, right? That ETL should be purpose-built. It should be like data store specific, then generalized where you support like thousands of connectors, right? So that was a very important decision. Second is obsessing over UX, right? So the thing is, this logical replication and logical decoding has so many pitfalls, right? Postgres can go down, ClickHouse can go down, logical decoding is not mature, it does not handle schema changes, right? Like, so there are like, replication slot could grow, it could get invalidated, right? Like, so there are like hundreds of all of these like edge cases that are around, right? So we really like iterated over these edge cases, like the 2 years of continuous iteration, right? I'll double click on how did we obsess over that UX as well. And last but not the least, which we already talked about, is like we leaned into Kubernetes for our managed service, right? And by the way, we do have Helm charts so you can use that, right? By default, it's Docker, but we also have Helm charts for PRDB, so you can use that. And also recently, one of our community contribution was like there is an operator also for PRDB, right? And you can use that as well, Kubernetes operator. So let's double click on what are the Postgres-specific optimizations which we did in PRDB and ClickPipes, right? So the first thing that we did is parallel snapshotting. And parallel snapshotting, what it does is, if you have a single large table, it logically partitions the table based on CTIDs. CTIDs are nothing but like physical location of a tuple, right? The actual physical location of a tuple on Postgres, right? They are in the form of, if you see, first is the page number and next is the offset, right? You have 0, 1, etc., right? What we do is we partition that table logically into like CTID ranges, right? It's a logical partitioning. We don't like create like actual partitions or something. It's just like logical partitioning, right? And then we read those logical partitions in parallel, right? And put it to ClickHouse, right? And we use S3 and like ZSTD compression, right? We also use cursors in between. That's very, very important because like, it should be streaming, then like, pulling, right? So we use cursors and that also helps, right? And then the advantage of this parallel snapshotting is it moves terabytes within hours instead of days, right? So we have customers like who move like tens of terabytes in few hours versus days. And you can configure the parallelism, right? Like, okay, I want to do 8 tables in parallel and I want to do 8 parallel threads, right? So that's all based on like how much resources you have on Postgres. If it's a read replica, you can use more, right? Like, so it all depends. Our defaults are like less aggressive. I mean, we use 4-1, like 4 threads and per table and 1 table in parallel, basically, right? So this is one optimization. And this one to battle test and mature did take quite a lot of time, right? Because here there are so many like failure scenarios, right? So when we used to, when customers used to test it, they used to fail here. Temporal did not send a heartbeat. There were like many edge cases here, right? Like, and then we over time it got battle tested, and you know, because retries are also very, very important. Things could fail. For ClickHouse is down for whatever reason. ClickHouse is ooming. PeerDB itself is ooming, right? All those cases we need to take care, and it did take some time for it to mature. Now, you know, it's all self-serve. Customer comes, adds like, you know, I have a Slack channel where like we continuously keep getting, okay, every day there are like many deployments, which all is self-serve basically, right? The second Postgres optimization is basically always consume the replication slot. This is very important for logical decoding and logical replication, right? The reason is because if you reconnections, when you do, when basically your client reconnects to Postgres for reading the replication slot, it reads from the restart LSN, which is the start of the write ahead log, right? And if you have a long running transaction, which is very large, that itself can take a long time, right? So what we do is we never give up the replication slot. In the initial design of PeerDB, we were doing it more like in batches, right? And that is something that I pushed the engineering team, and finally now, you know, if you look at the PGStat activity, we have the start replication running for like months. You'll see like some 1,000 hours, right? Which is actually good. That won't like block anything, right? You want to always consume the replication slot. That was an important decision, right? And also flush the replication slot because the pull and the push is decoupled, right? So we read, continuously flush, continuously send acknowledgements to Postgres that like, hey, I've read until here, I've read until here, so that Postgres flushes that slot basically, right? The third, interestingly, there is a LinkedIn discussion that's happening right before, 1 minute before the talk, is we do provide Postgres native monitoring, right? Now, whatever be it, there could be issues where logical replication slot grows, right? There is a long running transaction, we cannot do anything about it, logical replication slot grows, right? So we provide like, you know, visibility into basically how large is the replication slot over time. If that graph is like growing, it means that something is off with the database, right? It could be either like a product issue, it could be a, you know, the workload related issue, right? And then we also give you like, what's the state of the slot? Is it active or not? So if green means active, red means like not inactive, right? The start LSN, the restart LSN, the commit LSN, what's the lag, blah, 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 right? And then we also give you visibility into wait events, right? Here if you see the start replication, what are the wait events, right? Like it's a basic view of PGStat activity, but it's helpful to customers, right? And apart from all this, which is not captured here, is we have alerts also, right? So whenever like the replication slot grows out of threshold, right? Like say 50 gigs or something, we send an alert to the customer saying that, hey, something is off, and one documentation on, okay, how do you fix it, basically, right? So this is another Postgres-specific optimization. Now let's double click into the second decision, which really helped us, which is obsessing over UX. The first is when customer creates the pipe, right? We do a lot of validation, right? What I mean by this is there are many pitfalls even before creating the pipe, basically, right? You have stuff like my replication slot, I cannot connect to Postgres. I don't have the right permissions on Postgres, right? I don't have right permissions on ClickHouse, right? There are around 50-60 cases where customers can, you know, run into issues, right? We don't want the replication job to start and then silently fail, right? That will be a very bad experience for the user, right? So what we do is we have several validation checks which will actually surface the error before the customer starts the replication, right? So that like, okay, if permissions are not there, they can go and run a grant command and they can like fix it, right? So we try to like surface it as much as possible upfront, And this was a very iterative process, right? Like when we started it, now also we see sometimes that, you know, the replication job starts and the pipe silently fails, and I don't like that at all. I mean, like we immediately fix it, basically, right? So I also put link to our validate.go in open source, and that captures, it's a simple switch statement loop, nothing complex. It captures what are all the edge cases, right? Then the second thing which I was talking about is issue-specific notifications, right? So now logical decoding has like around many pitfalls, right? So what we do is whenever a customer runs into an issue, right, we see whether it's a user-related issue or a product-related issue, right? And then we classify, if it's a user-related issue, we basically notify the user right away with proper links to the documentation on how they can fix it, right? This is very important to scale, right? Like, I mean, first 50 customers we handheld them and it was fine, but then now we have 500 plus customers who like do like every possible thing. We need to scale. This really helped scale our support on call. Believe it or not, like we have a handful like team who does all of this, right? And also it gives full visibility into, you know, what's going on for the customer, right? Here is an example of replication slot size, right? So here we say that your click pipe is cross the replication slot size of 468 gigs, basically. The default is 50 gigs. Maybe for this instance, our people set it for like 400 gigs or something. And then we send a notification to the customer. And then we also send a doc, right? Like which actually says what are the reasons. The most common reason that I have seen is is basically long running transactions. That's what like I have seen for replication slot growth. And I'll talk about how that can be addressed. That's a future roadmap item. But we also send issue specific notifications. And then granular configurability, right? So customers want everything, right? Like they want to add a table, they want to remove a table, they want to specify, they want to replicate only these 2-3 columns because like on the analytical database, like they don't want to put PII data, right? It's possible, right? And so they want to pause, they want to remove a table. So like there are many you know requests that we got, right? And so we provide granular configurability to the customer, right? We also interestingly provide data modeling on the ClickHouse side. If you see there is the replacing merge tree, you can specify the table engine that whether it's replacing merge tree or the null table engine, right? You can also specify the custom sorting key. Custom sorting key is like the skip index in a ClickHouse, right? So we provide data modeling related items also to customers, right? Today morning there was an interesting request from one of our customers that they wanted to preserve nullability on ClickHouse, right? ClickHouse by default doesn't use null, okay? It's a columnar database. It stores at 0, -1 or whatever, right? Because for speeds, right? So you need to explicitly define that, hey, this column should be nullable, right? So there is a config that we provide which actually preserves that nullability. What it does is it goes and sees the Postgres columns, right? Like simple Postgres columns, C1 is not null, C2 is null. If C1 is null, we go and like, you know, preserve that nullability, right? And that needs to be handled when new columns are also added. So that's also one thing to keep in mind. So there are many edge cases that like we try to we handle and also give configurability to the user. And now let's get into what are the big gaps and what's next. Okay, I think we have 5 minutes. I'll quickly go because I have a surprise at the end. So big gaps are first lack of comprehensive support of schema changes. This everyone knows, right? Alter column default logical replication slot does not capture. Next is sub-second replication is not yet possible for ClickHouse. It's more in the 5 to 10 of seconds range. Customers want it because they want feedback in their real-time customer-facing application immediately. This is not warehousing, right? This is a real-time customer-facing application, right? That is one. Replication slot growth remains a common operational concern. One of the things that we plan to support is this logical replication V2, which will actually consume in-flight transactions, right? And that we have seen drastically flushes the slot in a much better way, right? It improves slot flush. There is a blog that we wrote, and Kevin, who is in the audience, gave a talk about it in PGConf India last time on he benchmarked logical replication in V1 and logical replication V2, and the differences are like eye-opening, where you know once you use logical replication V2, the slot flush is like 2 to 3 times better, basically, right? Logical decoding is single-threaded. This is a problem in the LinkedIn thread right now, right? Like, you know, there is a comment that, you know, PRDB is not able to cross some specific, you know, throughput. in single, we see around 20 to 30K per second from a TPS, not more than that. If you want more than that, create more replication slots, right? So this is a problem. Differences in data modeling between PostgreSQL and ClickHouse. This is a gap that we want to continuously bridge, because ClickHouse is a different database. This is not nullability, right? And updates are different, right? So we are making a lot of core improvements so that users, like the cognitive overload for users while data modeling is reduced. So one thing I would like to call out is we did launch our Postgres managed by ClickHouse. Yesterday I talked about it. It's a managed service that is deeply integrated in ClickHouse. It provides a one stack for OLTP and OLAP. So you get the best of both worlds, Postgres for transactions, ClickHouse for analytics, with no operational overhead. So the CDC is automatically included. You get a unified query layer for making it easy to build your applications. So and then you can try out our managed service using this link. And tomorrow, one thing I'd like to also call out is there is a meetup, ClickHouse meetup, where I will talk about this Postgres managed service. It's at 10:30 a.m. and feel free to join the meetup. With that, I will pass it to Kevin. There is a last-minute surprise. Kevin, can you try to cover it in 5 minutes, like 3-4 minutes?
No guarantees.
So basically, what we are doing is we will get into the state machine and show you how the state machine looks. We'll look at temporal. We'll look at like the states like very quickly. And can we take 3-4 minutes?
Yeah. Okay. So we'll just quickly cover the state machine that Sai talked about, to show like the different phases of a mirror. So everything's running locally. This is the PeerDB UI. That's the open source PeerDB UI. And we have a Postgres table that contains, it's like a 1.5 GB table that contains 20 million rows. So I'm going to start a mirror locally to just move this data to our local ClickHouse instance. Okay, that didn't work. 1 second, expected.
This is the validation, right? I was saying that like the table exists, it actually errored out right away, saying that the table exists.
So I think it did, okay. That was because, okay, so yeah, the table is started, the workflow started now. Mirror failed, okay. The demo is not going great. So Sai did tell us a surprise to me as well. So let's see what the mirror failed. No idea. Okay, let me just drop it and try again.
We'll give it one last try. If not, we'll send it.
Yeah, we'll. Okay, it worked now. Okay, cool.
Okay, awesome.
So we started a mirror. The mirror is, so this is a temporal workflow that is the root. So now as long as the mirror is running, this workflow will be running. And this workflow, this is the temporal UI that's also available in open source temporal. This workflow now kick off smaller workflows to do specific steps of the mirror. So we go to the first step. This step is setup flow. So this, you can see here like each activity it runs. An activity is basically a step of the workflow. And what we can do in temporal is I can see step 1, step 2, step 3, step 4, step 5. And another cool thing about temporal is you can reset the workflow. So now if I want to go back to an earlier step, I can just say, go back to this event. It'll rewind to this earlier event and run the workflow from there onward. So in case you have had customer issues where this step is failing, we can go back to an earlier step, fix itself, and then go back to a later step. And now you can see the entire workflow has this input. That says, table name, some other config parameters is all available. So now when you debug things, you just go to the temporal link and see what the input given to the mirror was. It's just to sort of see what the input of the mirror was. So this is the setup. It sees it, creates tables, it runs some checks, and then it finally finishes setup. This is just doesn't do any data movement. The next workflow here is a snapshot flow. So this is actually what that's the initial load phase. So it does some checks. So creates a replication slot, which is what Postgres actually uses to move data over to the destination ClickHouse. So it creates slots. It does some more checks, and then it spawns child workflow. So this workflow is actually a child workflow of the mirror, but it spawns even more child workflows to actually do the data movement. So you can see it created a QRepflow workflow, which has these child workflows that actually do the data movement. So if you go to one of these, partition flows, they are responsible for processing one partition of the table. So they move some a part of the table to ClickHouse. So there's 4 partitions, it's all configurable. And then it moves its partition and there's information about the partition as well. So it sees this partition, yeah, like you can see the ranges here. So it says this partition, you need to move this data, this data with this partition range to ClickHouse. And this is what it does. And after it finishes, this exits. So now we can go back to the mirror and we have seen that it has moved the 20 million rows in, I don't know, maybe like a minute or 2. And now if you query ClickHouse, we have our 20 million rows on ClickHouse. Now this is the next step. We will actually insert more rows. We will insert 1 more million rows. Cool. So we inserted more rows. This is the mirror in CDC. So now the snapshot is done. The mirror is actually reading the slot. So if you go to the Postgres peer, you can see it's reading the slot. It says active, yes. It says the restart LSN. So it's showing the pointers here as well in the UI, like where we currently are, how much we have to read as well. The slot lag is a parameter that says, you know, how far behind the latest position in Postgres we are. So we have to read 122 more MB of data to get to the latest point in Postgres. So you can also see, you know, connections here that we have to Postgres. Now if we go back to the mirror, we have moved 1 million rows. So it detected the changes and moved the 1 million rows to ClickHouse. And if we read ClickHouse again, we have 1 more million rows. So this is basically just a sneak peek because of lack of time of how the state machine works. So basically we have a mirror. That mirror creates setup flow. Setup flow does its work, it exits. Snapshot flow does its work, it exits. And now the mirror itself is running. It'll keep running forever. And it'll always read the changes and sort of move changes to ClickHouse as it sees. Thank you.
Yeah, awesome. Thank you.